Good morning. So in last week lectures, which is already posted in the Blackboard, we talk about single phase transformers, right? So the equivalent circuit of an ideal single phase transformers is basically two sides. So that's a coil, and this is another coil, and here we are drawing two sides. Now this side is called the primary side of a transformer, and this side is a secondary side of the transformer, right? Now, it's just a number of turns for every coil, so there are number of turns here. I'm going to call them NB, and B here is standing for primary. And in this side, we said this is the secondary side, so we're going to call the number of turns here NS, right? So NB is primary number of turns, NS is secondary number of turns, right? Okay. And as we learned from last week lecture, there is no physical connection between a primary side and secondary side. The power is transferred through induction. Here, this is the primary side. In the primary side, we connect the source of the power. That could be a transmission line system, that could be a distribution substation, and so on. Or a source, normal source, right? So here we're connecting the source. So this is the incoming side of the transformer, and this is the outgoing side of the transformer, right? So outgoing here will be connected to the load or another side of a transmission systems. Okay? So simply here, let's put a source, so we can connect a source here, right? An AC source, and here we will connect a load. That's a load, right? And this load could be a resistive load, could be RL load, like motors, for example, inductive resistive loads, equivalent circuit of motors, and so on, right? So here we're going to be focusing on the transformer side here. So the voltage in the primary is EB, and the voltage in the secondary is ES, right? So once you connect them, there will be a current here that flows in the primary, that's I primary, and here a current that is delivered to the load, and this is I secondary, right? So note that in the primary side, we use P standing for primary. This is the voltage in the primary side. This is the current passing through the coil of the primary side, and that's the number of turns N of the primary side. In this side, that's the number of turns in the secondary side. That's the voltage output of the secondary side, and that's the current flowing in the secondary side of a transformer. This is an equivalent circuit of ideal single phase transformer. We ignore the losses, right? We are assuming that the losses here is very low, because typically efficiency for transformers could reach up to 95-96%. So if it's acceptable to neglect the losses here, especially in low level transformers, right? So that's the ideal circuit of transformer. Okay, what's the relation between voltages and current? Remember, the transformers does not generate power. No, the transformers, from its name, just transforms power from one side to another side. So whatever the power is coming here will be transformed to that side, of course with some losses, right? But we're assuming that that's an ideal case, that's an ideal transformers, so we ignore the losses. So in general, typically we're saying whatever incoming power here will be transformed to the secondary side. Based on this, the power that is coming from here, we're gonna call it S, right? So this is S primary. That's the apparent power in volt ampere that is supplied from the source to the primary side and will be transformed to will be transferred to the load in the secondary side. So this is S secondary, right? Okay. Now what we are saying is that ignoring the losses in the ideal transformer, SB is equal to SS. So the volt ampere that is transferred by a transformer is same. Keep this in mind because we're going to use it for one equations later. Now, what is the relation between voltages, currents, and number of turns? Basically, that's the golden equation for transformer that everybody should know it. For an ideal transformer, the E secondary over E primary is equal to the percentage of N secondary over N primary, right? Cross multiplication will give you what? ES NB is EB NS. That's the cross multiplication. So ES over EB is equal to NS over NB. Be careful. We are not saying this doesn't mean ES is equal to NS. No. Or EB is equal to NB. No. That's basic math. The ratio is the same, right? Now current is opposite. Since we said in the beginning that it's the same power that's going to be transformed, now if you change the voltage, the current also should change, right? If you step the voltage up, if you raise the voltage up, what should happen to the current in order to keep the same power? It should go down. It should be stepped down, right? So that's why you will notice that the relation is opposite. Here ES over EB is equal to NS over NB is equal to IB over IS. See? The ratio of the current is opposite to the voltage, right? Now if you do cross multiplication here between this one, this ratio and this ratio, we're saying that EB times IB is equal to ES times IS. What is this? That's the apparent power, right? Magnitude of the apparent power, if you remember from three-phase circuit lecture. S in the primary and this is S in the secondary, and we are saying that they are equal because we ignore the losses. That's the golden equation of an ideal transformer that everybody should know it. Okay? Good. Now, this is single phase transformers. One coil. That coil is supplied by one source, and the coil here is transforming power or delivering power to one load. Right. Now, let me bring another two transformers to the system. Right. And we'll do something here. Yeah. So, this is one single phase transformers, and I'm gonna bring another single phase transformers identical with this, the same number of turns of ratio. Okay, right? See, does this remind me of something from lecture of week 9, right? Now what we're doing here, we are connecting a 3 single phase transformers in Y shape, in a star shape. You see, this is number 1, this is single phase transformer, another single phase transformer, a third single phase transformer. We do this in the primary side. Let's do it also in the secondary side. So I need some space here. Let me just make it full because we need some space here, right? So this was the secondary 2, right? So we're gonna bring another 2 as well, right? So this is here and this is here. Okay. Now, what is this in front of us? That's a Y to Y connection because this is the shape of Y from 3-phase circuit lecture. This is another shape of Y. This is now a primary side, this is a secondary side, which means the number of turns here is NP in a primary. The same thing here, NP, NB. In the primary side, they have same number of turns. In the secondary side, this is NS. Number of turns is NS, 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 right? Here we have a 3-phase incoming transmission system, for example, transmission line, or a 3-phase source connected to the primary, to the input side. That's the input side of the transformer. And here, this is 3-phase secondary side is delivering the power to 3-phase load, which could be 3-phase motors, for example, or outgoing 3-phase transmission system, right? So basically here it's the same idea, but now instead of having single phase transformers, we have 3 single phase transformers that we connect them in a shape of Y. If you focus on this, this is Y to Y connections, right? So the first connection of a 3-phase single phase transformers is Y to Y connection. or we call it star to star connections. So the primary side and both the secondary side are connected in Y shape. Good, great, okay. So let's put the equation. That's it. What are the relation between primary and secondary? So remember from three-phase circuit lecture. Now I'm gonna call this one A, B, C, for example, right? Or let me make it A, B, C. So let's say this is A, this one is B, and this one is C. And that side, let's make it small, capital and small. So this is gonna be A, and this one here is B, and this is C, right? This will be connected to a three-phase load, and this is supplied by a three-phase source, like three-phase substation, okay, or a three-phase transmission system. Primary side, secondary side. What's the relation between a primary side and secondary side? Easy, right? So let's just put the equation based on our golden equation for single-phase transformers. In the three single-phase transformers, we're going to be focusing mainly on the line-to-line voltage in the primary side and the line-to-line voltage in the secondary side. What's the relation between them? So from A to B, that's line-to-line in the primary. C to A, another line-to-line in the primary. B to C, that's line-to-line in the primary. These three line voltages from three-phase circuits lecture are equal in RMS values, but they have shift of 120 minus 120 magnitude based on the sequence. The same thing here. The voltage between A and B, that's line to line in the secondary side. B to C, line to line in the secondary side. C to A again is line to line in the secondary side. And these three line to line secondaries are the same in RMS values, but they have a phase shift of plus minus 120. Here we're going to be focusing only on the RMS values, right? RMS values. So what's the equation here basically? Equation of Y to Y connection is from the single phase golden equation that we've just shown before, E line to line, S which means secondary, over E line to line, P primary, A line to line in this side. For example here, from here to here, this is E line to line. It's E A to B, right? This one is E B to C, right? And from here to here, this is E C to A, right? All line to line voltages in the secondary side. It's in the secondary side. They have the same RMS values, the same values, but phase shift of 120 minus plus 120, right? So forget about the phase shift. Now we're going to be focusing here mainly on the RMS values. The same thing here. This is the voltage here, A to C. So this is CA. This one is EBC, for example, right? And from here to here, this is AB. These are all line to line in the primary side. In the primary side. Now, what in the primary side? They have the same, again, RMS value, phase shift of plus minus 120. Now, let's focus on the RMS values and the amplitude, the magnitude here. What is the relation between this voltage in the primary side and this voltage in the secondary side? In Y to Y connection, easy. The simple relation between them is coming from the Thevenin's ratio. Right? So let's go bring our equations from single phase transformers. E line to line secondary over E line to line primary is equal to number of turns in secondary over number of turns in primary. Okay? So from here, what we can conclude here, from here, what will be E line to line secondary? E line to line secondary is what? Is NS over NB times E line to line primary. That's the equations. See? And because it's Y to Y connection, there will be no phase shift between this voltage and that voltage. There is no phase difference between them, right? Because it's Y to Y connection, okay? But let's focus here on the RMS values. Of course, there will be some phase shifted between this voltage, and this voltage in one side, right? Which is plus minus 120. There will be some voltage phase shift between this voltage, and this voltage, because again, it's a plus minus 120. But if you would take this voltage, for example, ECA here and ECA here, they will have no phase shift difference because it's Y to Y connection. But the amplitude will be different. The RMS value from primary side and secondary side will be different based on the turns ratio. How many turns how many turns we have in the primary side and how many turns we have in the secondary side, right? So that's your golden equation for Y to Y connection. Okay? Good. Now based on this, what about the currents? The currents will be just opposite. So the I line secondary, the I line there secondary is MB over MS I line primary. Okay. This is true only in Y connection. Now this configuration is rarely used actually due to the problems of unbalanced voltage, potential unbalanced voltage and third harmonics and these things. So, but it is used, it's still there, right? So that's the first type of three-phase connection of transformers, star to star or Y to Y. The primary side is Y, the secondary side is Y.